Thank you so much. Thank you so much, everyone. My name is Enoch Nkoma from Malawi, Telecom Malawi, the telecommunications company. Um, so in this presentation, we just want to discuss how we implemented real-time analytics on Telecom CDR, but with emphasis on Apache Doris as our database engine. And we also want to stress how all of the components of our system are purely open source. So just a brief background to who we are. Telecom Malawi is one of the major telecommunication companies in Malawi. Actually, we have two. So TNM is, we have more, but TNM is one of the two major ones. And at the moment, it's the only one offering 5G network services in Malawi. It's been around for quite some time, since 1995. And just as any other telecommunications company, we offer voice, SMS, and data services. So for the just to explain a bit of roles setup and the organization structure this side, the data engineering function is part of the information service division, IS division. So within the IS division, we have the department known as Business Intelligence Department, and that department is responsible for all revenue reporting, analytics, but of importance, it also manages the relevant data platforms that helps them to achieve the reporting and analytics. Hence, this presentation is coming from that department because we are also the key players in the development and maintenance of the data platform. So a little bit of context and history. I think unlike most of the user stories we've heard, they're usually migrating from a modern data platform to a more modern and data platform. But our case is quite different because we are moving from a very traditional way of doing things to a modern way of managing our data. So we might say this is our first attempt to modernize our data platform. So where are we coming from? The current data platform that we have, that we are replacing with the one we've developed on top of Apache Doris, has been around since 2015. So it's been able to service the business for over a decade, been able to serve its purpose. And as I said, it's a very traditional data platform. We have got an Oracle database and then some custom ETL scripts to load data into the database. We also have some scheduled cron jobs that are triggered by, orchestrated by Apache Airflow. We've got an integration to internal SMS gateway for alerts in case of any failures within the pipeline. And for our BI2, we are using QuickSense for data visualization and the like. So what prompted us to think of modernizing our data platform? We noticed that the database that we are running on is an OLTP database, primarily meant for transactions processing, but we are using that database to run analytics. So some sort of misalignment that we wanted to correct. And also with the growing subscriber bases, the growing customers, the growing products that we are offering, the amount of data that the business generates keeps on increasing. Now, this makes these very traditional systems slow and heavy and not able to deliver the business impact. And also, really, we just want to align ourselves with the AI revolution because we understand very well that to be able to properly apply AI, we need to make sure that our data platforms are capable of implementing such AI use cases. So really, this has been a transition to modernize our data platform. So this was our objective when we started this project. In simple terms, to modernize the data platform. But then it was not just some random modernization attempt. We had goals or objectives that guided our system design and development. Number one, we wanted something that was of low cost and reliable. We understand managing cost is very critical to the business. To achieve the same, we wanted something that was open source and something that we could really scale and something that can help us power some AI use cases. And we really wanted something that was extremely fast. So in our first implementation of Apache Doris, what we are presenting today, the use case that we are focusing on was real-time analytics. So we wanted to design a system that is modern, scalable, of low cost, that will help us deliver real-time analytics to the business. So in our attempt to look for solutions to modernize our data platform, we encountered Apache Doris. So there are quite a few things that stood out to us regarding Apache Doris. For example, the success stories by the different users that were posted on the Apache Doris website. And some of those were really big companies with huge volumes of data. So it encouraged us that if they were able to use Apache Doris with those data volumes, we can equally do the same. And also something that was significant to our choice in using Apache Doris was the engineering philosophy behind Apache Doris. I think it resonated with our own engineering philosophy, making it very easy for us to adopt it into our environment. Also, we noticed that it was very easy to use and very easy to deploy just by looking at the documentation. And something that was very critical as well was on smooth transition. We understand it's our responsibility as well as data custodians to ensure a smooth transitions whenever you change the underlying technology. So here we have a number of people running queries on the database. So we wanted something that if we were to change, they should still be able to do their things using the processes that they already used. That's when we discovered that Apache Doris is 100% MySQL compatible, which will definitely ensure smooth transition and business continuity. The users are already familiar with MySQL, SQL, so it should be very easy for them to use Apache Doris in a MySQL environment. So that's what prompted us to immediately try out Apache Doris. So in our design for this modern data platform, I think it was not rocket science. It's just basic system design principles, modularity. We wanted to build a system that can be split into independent and interchangeable modules. We understand things are always changing. We could easily replace one module with a better implementation and so forth. And also, as I mentioned earlier, the number of users, the number of subscribers in the network is growing, the number of products we offer is growing. So likewise, we wanted to build something that we could scale very easily by simply adding the resources. We don't have to break a lot of things um, to scale the system. And fault tolerance was also very critical. We understand the business relies very much on the reports that we will generate from the system. So in the event of failure, we want a system that should be able to continue to operate seamlessly, regardless of some failures or performance issues. And also observability. We wanted to build observability into our design. We didn't want a situation where we are blindly operating a system. So these are some of the principles that guided our design for this modern data platform. So this is an overview of the system that we built. Um, it has three distinct modules. We have the data ingestion engine and the database itself, Apache Doris, and also an external entity, the QuickSense that we use as our BI tool. Now you see everything is under Grafana for observability. We have Grafana dashboards and it's configured to monitor the health metrics of the individual components of our system. So I'll dive deep into each of these individual components, particularly the data ingestion and the all-up engine, so that we understand better our implementation. But as you can see from the overview, our Doris deployment, we use compute storage decoupled. That's why we have Hadoop as our object storage layer. All right. So in our data ingestion engine, we understood very well that to deliver real-time analytics to the business, we need to implement near real-time data ingestion to the system. Now, this would be quite different from what we've been doing in the past. We used to run some cron jobs maybe after midnight to load data from the previous day and generate reports. But now, as we move into real-time analytics, it is very critical that we implement real-time data ingestion into our system. So now we had a challenge on this because most of the systems that were to act as our data source internally do not have support for modern data streaming. They do not produce Kafka topics and something like that. So the operating model is that they dump the CDR files in a certain location, of course, in a near real-time way, but they do not have direct integrations to any of the data streaming technologies that are available today. So that was the first challenge. That how do we work with that kind of setup where data streaming is not natively uh, supported? So another issue that we are looking at in our data ingestion engine is the high volumes of data. So for the data that is dumped in near real time, I think we have about 70 million records that are dumped in near real time. And then we have approximately 300 million records per day that are dumped at the end of the day. So this could be customer balances, maybe other customer profiles, and maybe some data that is just dumped once a day. And then we also have mobile money transactions. So we needed to build a system that is very resilient and with high read throughput because we've got high volumes of data on the ingestion. So now solving the data ingestion problem was really trying to strike the balance between speed in terms of performance in terms of speed as well as avoiding duplicates, exactly one semantics on the data ingestion engine. So our data ingestion system that we designed is a very simple system using these two key technologies. We had Logstash and Apache Kafka. So the Logstash was coming in because we did not have that modern data streaming service in most of the internal systems. But then we had to work with the files that are dumped in near real time. So the Logstash, what it does, it simply collects those CDR files that are dumped in near real time, performs some preliminary transformations because the CDR files are dumped in a pipe separated manner. So we marry them with columns, maybe we change them to a comma separated version, and maybe a few transformations here and there. And then the Logstash creates a topic onto Kafka. So here the separation is on stream level. Each CDR stream has got its own corresponding pipeline in Logstash. For example, for the SMS CDRs, we have an equivalent SMS pipeline in Logstash. It collects the SMS CDRs, transforms them, and then pushes them into a Kafka topic. So on the Kafka, we retain the CDRs for 24 hours to allow for replays in case of any eventuality. So on Logstash, this was the configuration that we had using the file input to roll the CDR files, and we also had the Sense DB just to make sure that we are keeping track of each file read progress. And our Sense DB is something that we persisted on the disk. We didn't use memory DB. Likewise, for the event queue within the Logstash, we opted for the memory event queue instead of the persistent queue that will be saved on the disk. So we made this compromise, understanding very well that in memory queues, if, if, uh, if there is a crash, you lose all the messages that were still inside the filters and were not written to the out. But this was very good for us because of the speed and also losing those CDR messages within the Logstash operation may not be a big problem to us because we always have the CDRs from the source. We can always replay them from the source. So we made the compromise to use the in-memory event queue to improve on speed, to win on speed. Losing CDR messages was not quite a problem to us. And then on the Kafka, this was the setup that we had. So each on the producer side, we had each Logstash pipeline producing a specific Kafka topic, so be it voice CDRs, SMS CDRs, recharge CDRs, and the like. This is just a sample of the pipelines that we had. So each Logstash pipeline was producing a topic onto the Kafka within the Kafka blocker. So look, our Logstash deployment is cluster based just to ensure we have good high throughput there, and also our Kafka blocker is deployed in a cluster setup. And also something that was very helpful was partitioning of messages on the Kafka. We noticed that Doris does a very good job on this one. The moment you partition your Kafka topics, it automatically creates more tasks on the routine load consumers to ensure high throughput. So we partitioned our Kafka topics, and then Doris did the rest on its end to automatically create more tasks to ensure parallelism and high read throughput, so that we don't have any delays, particularly on the data ingestion there. So uh, putting our data now from the data ingestion engine into Apache Doris, there are two strategies that we're using. We're using the routine node. So the routine node, we're using it particularly for those real-time streams, those that are dumped in near real time, the CDR files that we collect. So we have got 9 distinct pipelines that are running on Doris routine node. And then I think I mentioned this point already about Kafka topic partitioning and how it helps our Doris consumers to create more tasks and increase the read throughput. But the routine node is not the only data ingestion strategy we're using on Doris. We're also using the Doris stream node. So particularly, we're using this for the end of day dump. I did mention that there are other dumps that are created at end of day, be it customer balances and the like. So we're using Doris stream nodes to load those files. There are usually maybe 300 million records, 150 million records a day. And Doris stream node, we're using the client too and not the HTTP pure one. And we noticed that this one is very easy to use, and we are able to integrate it into our Apache Airflow DAG and orchestrate those load jobs onto Apache Doris. So, as I mentioned earlier, it was very key and critical that we don't operate our system blindly, and observability had to be part of whatever we were designing. So, we did come up with quite a number of dashboards to help us monitor our system. So, I'll start with the Doris routine node. We noticed that Doris comes with its own Grafana dashboard. It's just plug and play. You download and then you import into Grafana, and then you can monitor the routine load jobs. But I think what we wanted was something more detailed. We wanted to have more details about which job has failed, on which database is it running, something like that. So to achieve that, we had developed our own custom routine node export that will just run a query against the DB and then push that data to Prometheus And then on Grafana, we could get those details and we're able to generate SMS alerts in any events where any of those pipelines is down. So we wanted to capture the details, which job has failed, um, on which database, what's the state, and really any other recommendation that we can give to the monitoring team. So probably this is one of the um, custom main codes that we have added into the data platform. So the performance of our system is on the data ingestion layer is quite very good. We have an approximate delay of 5 minutes from the CDR creation time onto the load time. So by that I mean an event happening on any of the network systems, it takes about 5 minutes before we can pick it up on our analytics engine. And that delay mainly is not because of our data ingestion system, but because of some mediation processes that happen within the internal system. The subscribers are split across nodes, and then those files have to be collected from the various nodes and then dumped into one location where we can start to process them. So all that delay is outside of our data ingestion engine, but we have about 5 minutes delays on that. So maybe I can just share this dashboard, a custom dashboard that we built on top of Grafana to monitor Logstash performance. All right, so this is the Logstash monitor in our test environment. So there are several metrics that we look at: the CPU usage and maybe the events per pipeline across time. But I think this is something that we also try to monitor because it tells us the health of our downstream systems, the back pressure in the pipeline. The moment we see a spike on this dashboard, we know immediately that there should be something wrong with our downstream systems, being Kafka and the like. So this is a dashboard that we built just to keep an eye on our Grafana instance as it runs. Let me go back. All right, so this is just a summary of the data ingestion engine as I was presenting it, where we have got the data source system, then we have got a log stash pipeline processing each stream from the data sources, being an SMS stream, a data stream, a voice stream, and then here we indicate that our deployment is containerized. We have Docker just to make sure we are able to properly manage this service. And then from the CDR collection service, we call it, we push that data onto our Kafka cluster. And then each pipeline on the Logstash is pushing to an equivalent Kafka topic. And we've seen that this setup is very good because we've been able to service other business stakeholders from the Kafka layer, for example, maybe integrations to the CVM. Instead of them going directly to the source, they're able to obtain some very important data from our Kafka cluster. And then we have got the Doris routine load for real-time rolling in. And then this was supposed to be the steamroller for end of day dumps, balances, and other data that we load. So this is our data ingestion engine. Then if you remember from the beginning, I said we have two components. The other one is the database engine itself, Apache Doris. So a few notes on how we deployed Apache Doris. Our deployment, as Sherry mentioned in the introduction, we deployed the storage compute decoupled deployment. And then the version that we are currently running is 3.0.7. And then we've seen some benefits from this deployment, the compute storage decoupled deployment. But maybe Let me explain the architecture diagram before I go into some of the benefits that we have realized. So as you may see from the diagram, we have got three host machines that are running our Doris node. So these are all virtual machines, but this is the physical host. So what we're trying to depict here is that we have split our, our nodes across multiple physical hosts just to ensure fault tolerance. For example, we have got Kafka on host 1, and then it is running on VA number 1 on that particular host. So should any issues happen to this host, it means we will be able to run on Kafka that is running on a separate host. So for the metadata layer, we have combined the FE node, the foundation DB, and the master service. Those are running on the same node. So as advised, we deployed all three, the master, the follower, as well as the observer node. And we have these split across the three hosts that we are using to deploy Apache Doris. So as well as the compute layer, we have got the backend split across the three hosts for the same reason. And then we have got Apache Hadoop on the other end, acting as our independent storage layer. So some of the benefits that we've seen is that because there are quite a number of people that run their queries on on the database that we produce. These could be people from other departments, maybe marketing, maybe revenue, assurance. And we really want to, because in our previous setup, we had issues where if people from other sections are running heavy queries, which are of importance to them at that particular time, they're very urgent, it will end up affecting other agents' operations that are happening to people in other departments. So we really needed a way to clearly separate the computing concerns of these different departments. And with this approach, with Apache, with storage compute decoupled, we've been able to do that properly because we have compute groups for the different business groups that wants to run their queries on our database. So everything they do on their side does not affect any operations that are happening on our end. And also, so that's the first advantage. The storage compute decoupled mode has helped us to properly implement the compute storage, the compute groups separation between the various business stakeholders. And also another benefit that we've seen is responsibility management, as it were. We have got a separate team that is responsible for managing storage. Anything to do with storage is their concern. It doesn't have to concern people that are managing Apache storage. And as a result, we plan to use Apache Hadoop for other use cases. At the moment, we're only using it as a storage bot for our Apache Doris cluster, but we intend to expand the use cases of our storage layer, and that will scale independent of our compute needs on Apache Doris. So that's something that we really appreciated from the storage compute decoupling mode. So something to do with data refreshing. So we've moved the data from the sources using our Logstash or Kafka. We've ingested into our Doris engine. We want to have a mechanism of refreshing our reports. So there are three strategies that we are currently using to refresh our reports. The first one is aggregate on load table model. We've seen that these are very great when it comes to generating summary tables. The moment data is being ingested from a Kafka topic, Apache Doris instantly um, generates summaries on those data items. No need for any other external scripts to be summarizing those tables for us. So we are utilizing the aggregate on node, but also we have got for some other specific use cases, we still maintain our Airflow orchestrated jobs to refresh some of these live tables periodically. And to achieve that, I think we've seen that table partitioning has been very critical so that we only refresh data for that particular day. Whenever the refreshing script is running, it only runs on the data for that particular day. So table partitioning has been very critical in this periodic refresh using an external tool. And also on our batch layer, so for the live reports, that's our live or staging layer, but for the batch reports, we still maintain some end of day jobs. At the end of the day, they are orchestrated by Apache Airflow, and then we perform some reconciliations with the data source, and then we run the summaries. So these are just end of day summaries that we run. So the end of day data, we retain it for quite some time as compared to the live reports that we deploy. So some of the things that we've been able to do currently, let me just show you this one. So I'll stop sharing my screen here and share this one. So this is one of the use cases from users internally, but from a different department. They are, they've used the CDRs that we load to monitor failure events on the billing system. So previously, this is huge data, something that we are not able to immediately process and get the insight. But because of how effective the real-time engineers deployed is, they're able to gain these insights to see that okay, maybe most of the failures that are happening on the system are due to insufficient customer balances and other use cases. So they have the expertise to know that okay, maybe this spike has to be monitored. There should be something wrong with the system. So aside from the revenue reporting that we do, how much sales we've made per day, and the like, our use cases seems to go beyond revenue reporting. We can see other users have already developed this dashboard to monitor the health of their external system using the same CDRs that we are loading onto the system. Let me share something else. Okay. So we understand that our developments on Apache Doris are still in their very early phases. This is our first year. Our primary target this year was just to deliver real-time analytics to the business, revenue reports, as well as system monitoring, as I've mentioned in the previous use case. But now, looking ahead, we want to mature our use of Apache Doris. We want to now try out some AI use cases. We want to try predictive analytics now that we've closed the real-time analytics chapter. So we look forward to being part of the Apache Doris community. We look forward to contributing to the community in whatever ways we can, and really just keep the community growing because we understand that Apache Doris is one of the greatest things that has ever happened to us as data engineers. So we look forward to a bright future where we continue our development on Apache Doris. Thank you so much for your attention and patience. I think that should be the end of what I prepared for you guys this morning.